All right. Y'all doing good? Yeah? Okay. We have an exam a week from today. Sorry. We have an exam on Thursday. Today we're going to cover 7.6. 7.6 will be on the exam. And I'm hoping that once we get through 7.6, you'll kind of like the idea that it's on the exam, because it's not like 10 different topics. It's kind of one idea. And if you can get the idea down, then it should benefit you on the exam. It should be a problem you should be able to handle. Okay? We'll see. I do have your quizzes from the take-home quiz. I did grade it. I did post the grades on Canvas. I will pass out the sign-in sheet, and you can just go ahead and take your quiz when the packet comes around. Okay? All right. Any questions over homework? I did not get the homework video up. This semester's just, man, I just cannot seem to get ahead. It's always something. My daughter fainted at school the other day. I was getting ready to do the videos, middle of the class, or middle of my office hours. I was getting ready to do the videos and get a phone call. My daughter fainted, so I had to go and leave. And so I've just been behind. But
okay?
She's fine. I don't know. Weird. So, anyways. Yeah, so any questions on the homework that you want me to go over? No? Okay. All right, let's get down to business then. We are going to talk about graphing sine and cosine. And what I want to say here is that the way the book does this is they talk about graphing sine and cosine with certain kind of restrictions. And then later on, we add a little bit more junk onto the graphs. And so when I'm teaching it, I'm looking at it from the perspective of what you're going to need to do later. So I'm trying to give you a method today that's going to work even down the road. The way the book does it, I think you almost have to look at it as two separate methods, and I don't like that. I'd rather have one method that works for all scenarios. So that's the perspective I'm going to come from. All right, so graphs of sine and cosine. So we learned last time that if we define a function f of t to be sine of t, that is always equal to what? In terms of the unit circle, what was that? We have a unit circle coming out the x-axis here. It's the y value of the point. Okay, so if I pick some arbitrary point on this circle, doesn't matter where it is, and I construct an angle, standard angle that goes from the x-axis to that point, and we call that angle t, then we have a point that corresponds to this x and y, and sine of t that would then be always the y coordinate here, right? Does this ring a bell? Yes, yes. This is the unit circle, though, so I should make sure that I'm aware that that's a radius 1. Okay? Now, what we're going to do right now is going to be, it can be confusing, because right now in your mind, x and y are the x and y coordinates, right? Yes? But in college algebra, when we were defining functions, f of x, like x squared, x was the independent variable. That was the thing we were plugging in, right? We were plugging in the x and it was spitting out a y in this case. But in terms of a function, this is the input and this is the output, right? So here, our input is what? What letter is our input? T, and the output is y off of this graph. It's the y coordinate, right? But I could call that t anything I want. I could have relabeled this, theta, and then that would be f of theta is sine of theta is equal to y, right? So to get back more to the more traditional notation for functions, what I'm going to do is I'm going to call this x. Now that's confusing because you might want to confuse it with this x. That's not what it is, all right? We're looking at this more like just purely from an algebraic standpoint. If I define a function f of x to be equal to sine of x, then you still in your mind want to have this picture that this is going to give you the y coordinate off the unit circle if your angle is x. Understand? It has nothing to do with this x right here. Are we good? Yeah? Okay. So let's see. If I were to do this and create a t-table, we did this last class, we created a t-table. The input was here, the output was here. Let's get just a couple of values so we can try and, I want to graph the sine function. That's what I want to do. And that's why I'm using f of x, because that's the way we've always graphed in the past, right? F of x is x squared, f of x is square root of x, f of x is some quadratic function. X has always been the independent variable. So I'm trying to stick to that convention. Get rid of the t. So sine of 0, is the y coordinate off the unit circle if your angle is 0. 0. Okay. Let's not pick every common angle. Let's go to the nice ones. How about pi over 4? Sine of pi over 4. We're here, right? The y coordinate should be root 2 over 2. By the way, on your calculator, could we just real quickly type that in and just see what that is approximately as a decimal? You should get about 0.707, I believe. Yeah, something about like that. And then the next nice angle, how about pi over 2? We're at 1, right? That's straight up. The next one would be 3 pi over 4. What's sine of 3 pi over 4? Root 2 over 2 again, which is about 0.707. Let's keep going. Pi, sine of pi, 0. How about 5 pi over 4? That's down here, right? Like this. Negative root 2 over 2. It's approximately negative 0.707. And then 6 pi over 4 is same as 3 pi over 2. So now we're straight down, right? Straight down. The y coordinate there is negative 1. And then 7 pi over 4, we're almost all the way around. 7 pi over 4 is again negative root 2 over 2, right? It's 0.707. And then finally we come all the way around. We're at 2 pi, and we're back to 0. And then pretty much from here on out, if I keep going around now, right? If I keep on going around, I'm going to just repeat that table, right? So we're now going to kind of take this picture out, and we're going to try and draw this graph like we would any function. F of x is x squared. F of x is square root of x. We're just going to draw our x-axis, our y-axis, and plot it. So what we should get, is something like this. So here's our x, and here's our f of x, our output. Now what can you tell me the maximum up and down is going to be here? The highest it will ever go should be 1, and the lowest is negative 1. We talked about that, the range of the sine function last class. So this should be 1 here, negative 1. And now let's start plugging in. At an x value of 0, it spits out 0. So that's like an ordered pair, right? 0, 0. And then we could just go to the next point, right? Pi over 4, mark it out, and then put a point. I'm going to do this a little different, though. I'm going to actually start at the end, the last point. I did this first point. Now I want to do the last point. The last point would be out here somewhere, right? And this distance right here would be how far? What is the x value here? 2 pi. Is that what you said? I didn't hear. I thought I heard something else. 2 pi. Now 2 times pi on your calculator is like 6.28 or something like that. But I'm going to leave it as 2 pi. So if we go out to 2 pi, what's my y value here? 0. Okay? There. Then what I'm going to do is I'm going to go halfway. Okay? So what's halfway between 0 and 2 pi? Halfway should be pi, right? And that should be, I have this on my table, right? That's 0 again. So if I'm trying to graph this function, I actually can see right now 3 x-intercepts, right? I have 3 x-intercepts here. Now let's cut these in half. Like what if I cut this in half? So what is, it should just push open. Huh? Halfway should be pi over 2. And what would halfway here be? What would halfway between pi and 2 pi be? That should be 3 pi over 2?
Yeah, I agree.
3 pi over 2. So really what we've done is we're picking out, let's see, this was the end point, this was the middle point, this was the other end point, right? And then we went to the ones that were halfway between those, which were these two, right? See those 5 points that I'm using here? Throughout the rest of the class, as I'm graphing sine and cosine, I'm always going to be trying to get 5 points. And once I have those 5 points, those are kind of my reference points, and I can draw the function, all right? But let me label this 3 pi over 2. Okay, so what was the value of this at pi over 2? 1. So if I go out to pi over 2, I should go up 1. At 3 pi over 2, negative 1. So you can kind of start to see this graph come to life. We're going to somehow go up, and then we've got to come back down, then we've got to go back up. Now, if we cut these in half, like what's halfway between 0 and pi over 2? Well, that should be this one, right? Pi over 4. What's the value of the function at pi over 4? 0.7-ish, which is more than halfway, right? So it'd be somewhere around here. I'm just kind of eyeballing that in. Y'all got that? Now, I didn't label this, but it's getting kind of tight here on my x-axis. Does everyone understand that's pi over 4 there? And then I have another halfway point, which would correspond to this one. And that would be 0.7 again, or 0.707. So that would be the same height, just the other side over here. Got that one. Then I could go halfway between pi and 3 pi over 2, which would be between here and here. The halfway point is this one, right? And it's giving me a negative y value of 0.707. So now I'm down here. And then if I go halfway here, I've got that same y value, just a little bit further down the x-axis. And that right there is enough for us to get a good idea of what this looks like. It would be a curve. It would go like this, come down like this, and come back up. And that picture right there, that little snapshot gives you a great idea of what the sine function is doing. Now, I could continue with more angles, right? Because when I go around one time, that's 2 pi. But I could go around it completely again, right? And go 4 pi. If I go out completely, one more rotation, one more full revolution, then I can extend my x-axis out again. 4 pi would be about right here. And what's going to happen? What will my picture do in that interval between 2 pi and 4 pi over 2? It'll just repeat itself, right? Everything's going to be exactly the same. So what I could do is take 2 pi and 4 pi, cut it in half. What would that one be? Halfway between 2 pi and 4 pi. 3 pi, right? And now I would like you to actually tell me what those points are. What are they in terms of pi? What's halfway between, I'm going to take this little x out of here. What's halfway between 2 pi and 3 pi? 5 pi over 2? How are you getting that?
Oh, we did it last week where the halfway interval means I wrote it down.
It's right. I'm not saying it's wrong. It's good. But I think we all need to figure that. I'm going to show you something because we all need a way of finding the middle of two numbers. It's not something that we think about too much. Like if I give you these two numbers, 3 and 5, and I ask you what's the number right in the middle, you're like 4, right? You just bat 4, it's no big deal. But if it's something like 7, what we do is we take the average of the two numbers. 7's still too easy. Let's go 8. What's the number right in the middle of 3 and 8? We take their average. We add them together and divide by 2. Always. 11 halves. Understand? Okay, so if I want the number that's between 2 pi and 3 pi, what I'm going to do is add them together and divide by 2. So I'm going to take 2 pi and 3 pi and divide that by 2. So that's going to be what? 5 pi's on top over 2. 5 pi over 2. That's this middle number. Understand? And then the number between 3 pi and 4 pi, 7 pi over 2, right? You take 3 pi, add 4 pi, divide by 2, 7 pi over 2. Right now, maybe this is not so big of a deal, but later on, when we take these sine curves and we move them, we shift them left and right. They call them phase shifts. When we do that, then those points are not necessarily going to be nice numbers to work with. Okay, so do you see that with what I've drawn, I had between 2 pi and 4 pi, I cut it into 4 equal sections again, which gave me 5 points, right? But 3 of them are x-intercepts. So I'm just basically reproducing this graph. So I should go back up, back down, back up. And then I could keep going, right? And I would have another one, it'd go forever. And then what about in the negative direction? Can we have negative angles? Positive angles go this way, negative angles go the other way. So we can have negative angles. And we would have to go backwards 2 pi, negative 2 pi, sorry. Cut that in half, we have negative pi. Cut each of those in half, negative pi over 2, negative 3 pi over 2, and then draw it this way. Now, it's just going to be an extension of this. So as we went down and then up, it'll go down again, back up, and then back down like that. And again, I have those 3 x-intercepts, don't I? Okay, so the sine function extends forever in both directions. In this particular case, the highest number is 1, the lowest point is -1, and it looks like the distance between the beginning and ending of the function before it starts repeating itself, that distance looks like it's about 2 pi, right? Pardon?
That's the focus.
We call it the period.
The period of the focus is the other part.
Amplitude.
Amplitude,
Amplitude?
okay. One of the words.
Okay.
I know there's 2 other terms for it.
Yeah, amplitude and period. Those are the 2 things we're about to define. But this is your standard sine function. All right? Any questions on how we develop that? All right. Now, from this picture, I think you can tell me whether or not you agree or disagree. The domain and range from this are a lot easier to see. We already know what the domain and range of sine are, but I'm trying to illustrate that it's easier to see it now because domain is what you can plug in. So if we look at the x values, if I go left or right, I've always got graph, right? So the domain can be anything. So we say that in interval notation, -infinity to infinity. And then the range are the y values, so we look up and down, and we have graph from 1 all the way down -1, so we write that actually the other way, -1 to 1 like that with brackets. So it's easy to see the domain and range once you have the graph. We also have what we call the period. And the period is basically the distance between, you could go from like the highest points, like here to here, that distance. Or you could go from lowest point to lowest point, like this, that distance. Or you could go from this starting point to this ending point. That distance right there is called the period. You can go from the highest point to highest point, crest, trough, trough, or you can go from this starting point to this ending point, where you get that one picture that just keeps repeating itself. That's called the period. And the period for the standard sine function, for this standard sine function, is 2 pi, right? That's the distance it takes before it starts repeating itself. Does everyone kind of agree with that? Mm-hmm. Now we also have another thing we measure here, which is the amplitude. And the amplitude has to do with how tall the function is. And we measure that It's actually the distance, I don't want to say from the x-axis because we might move this up or down later. But if you take the distance from the highest point to the lowest point, that distance, okay, and divide it by 2, that's your amplitude. Because what is the distance from here to here? If you measured that, what is that? 2 units, right? So your amplitude is actually half of that distance. Understand? So it's the distance from top to bottom. We can use more technical words, but I'm going to say from top to bottom. And then divided by 2. Old school division sign there for you. Couldn't you also say it's the range, the distance in the range divided by 2? It's kind of like this, like that distance is 2. From -1 to 1, that's 2, and then divided by 2. So the amplitude of the standard sine function is 1. We good? Questions? Comments? Did anyone see where that cap went? Oh, there it is. All right, I'm going to erase this, and I have a little animation to show you. It's basically everything I just put up on the board, but animated. Sometimes it helps students see it a little better. All right. Where was it? Okay, so here's the unit circle, right? And I'm going to start moving around the unit circle. The angle in here is x, all right? And what we're going to be able to do is see the y-coordinate over here. That's sine, right? Sine is the height of that point. And we're going to see that get mapped over here. And I think you can kind of see it get drawn. So do you see that the distance here is the distance here? But this is measuring this angle. That's what this is measuring. So as you move around, we go up, and then as the angle gets to 90 degrees and goes past 90, now your y-coordinate starts coming down. And then when we get past pi, now you've got a negative y-coordinate. And then you get down to the lowest point here, 3 pi over 2. You get to -1. And then you go back, and now your y-coordinate is starting to shrink down back to 0. That's where it comes from. See the connection? Okay. Now, we can do the exact same thing for cosine now. Right? We can do the same setup, but try and figure out what cosine looks like. So what is cosine? If you're on the unit circle, cosine of the angle is the x-coordinate, right? So do you see why now I especially need to make sure you're not getting the x's confused? Because if I define a function, f of x, to be equal to cosine x, x is the angle, right? But you're telling me that the value of this function is the x-coordinate off of the unit circle. We're talking about 2 different x's. So it's a little confusing, but we can do it. We'll try this one a little different. You know that little image I just brought up? Let's try and draw ours using that image, but we're going to do our own. Okay? Now, cosine should also repeat itself every 2 pi. Would you agree? Because once it goes around once, then it's going to have to do the same thing again. So I'm going to go ahead and I'll cut this here at 2 pi. And I'm going to do the exact same thing I did with sine. I'm going to cut that in half. I'm going to cut each of those in half, which gives me a total of 5 points again, right? 5 different points to evaluate the function. 4 equal sections, 5 separate points. Now, let's start at 0. What is cosine of 0? It's my x-coordinate right here, which is 1. So I'm actually going to start out at 1. Let's go all the way around to 2 pi. What would cosine of 2 pi be? So go all the way around. It'd be 1 again, right? So out here at 2 pi, it's back up here at 1. All right, let's go halfway. What would cosine what will cosine of pi be? So it would be the x-coordinate right here. Negative 1. So at pi, we're down here at negative 1, like that. And then how about pi over 2? Cosine of pi over 2. Pi over 2 is straight up, isn't it? What's the x-coordinate right there? 0. So I have an x-intercept right here. All right. And then how about 3 pi over 2? So coming down like this, x-coordinate here is 0 also. So I have 2 x-intercepts in there, don't I? The sine had 3, didn't it? This cosine has 2 x-intercepts in there. And now we could go and, we could do like, let's try this one. We won't go all the way around, but if we did the pi over 4 right here, what would the x-coordinate be at pi over 4? What's the x-coordinate here?
Square root of 2.
Root 2 over 2, which is about 0.707 something.
707.
So that means halfway between 0 and pi over 2, which is pi over 4, right there, halfway, I should be up 0.7. Like that. Let's go a little more. Here's pi over 2. Let's go halfway between pi over 2 and pi, which would be right here. What's the x-coordinate right there?
That's negative pi. That's negative root 2.
Negative root 2 over 2, so negative 0.707. So halfway between pi over 2 and pi, I'm now down here at negative. And we could complete the rest of this out, right? I'm not going to. But you can kind of see what's happening here. It's going to go like this, then drop down, and it's going to come back up and be like this. These are curves. These are not V's. Do not draw V's. These are not sharp corners down here. They are curved. And then from here, if we drew out to 4 pi, we would cut that in half, 3 pi, and then cut those in half. And we would get a repeat image, wouldn't we? Yep. So where are my x-intercepts going to be here? You don't have to tell me the number. Just tell me, is it the first, second, third, fourth, or fifth dash mark here? The second and the fourth. These are going to be my x-intercepts. I should have this highest point should be repeated at the end. Yep. And the negative 1 down here should be repeated there. And then just draw your curves again like this. So that's your standard cosine. Does it go backwards too? Yep. Yes, so it would go like this and come backwards. What is the domain of this? All real numbers again, so negative infinity to infinity. And the range? Negative 1 to 1. And then what about the period?
The period is going to be...
What's the distance between where it starts to repeat itself? 2 pi again, right? Look, highest point, distance there is 2 pi. So we get 2 pi for the period. And then what about the amplitude? This is 1 again. It's that total distance, which was 2, right? 2 units. Between here and here, it's 2. Take half of that, your amplitude is 1. All right, this section is just sine and cosine. We're not going to do tangent right now. But now we're going to start to throw some twists into the functions and see how it affects the graph. I think I have another animation, but this one is just to show you both the sine and cosine graph together. So if I were to, that's that same circle, right, that I was doing earlier. If I were to draw these together, here's what they would look like. Yeah, that's it. That's one period. So here, the red is the sine, and then the blue is the cosine. Ignore that straight line. That's just showing you where you are. But those look pretty darn close to each other, don't they? I mean, they look really close, and if we extend them in both directions, that's what they would look like. And notice that on the number line here, it uses integers, like 1, 2, 3, but on ours we use like 2 pi, pi. We said 2 pi was about 6 point something, so 6 point something's about right out here. Pi is 3.1415, so pi is right about there, and that is where that sine function hits. Now this little code here allows me to just change those over to pi's instead of integers, so you can see them a little better. Okay? Good? So it kind of looks like, it almost looks like you could turn cosine into sine if you just like moved it left or right, right? You could like lay one on top of the other, which we will do. All right, we're going to actually move them around. All right, so let's try this now. Let's do this example here. Let's graph f of x equals sine of, let's go with a nicer number for our first example here. Let's do sine of 4x. So the question becomes for us, how does this 4x impact our picture? Instead of just x, it's 4x. So what's it going to do to the graph, right? It's got to do something, right? It's got to change something. So I told you my thing here is to try and get you to have a technique that you can use down the road. So what I recommend you do is this. You say first to yourself, I'm doing a sine function, right? A sine function has 3x intercepts, doesn't it? When we did the standard sine function, it was like this. It had 3x intercepts. What I'm going to try and figure out is how I could first get the two endpoints. What I mean by that is, what would I have to plug in here to 4x, or what would I have to plug in for x to get 0 and to get 2 pi? So just follow me through here. I'm going to start with this. I'm going to take 4x, and I'm going to set it to 0, and I'm going to do a different equation, 4x, and I'm going to set it equal to 2 pi. All right? I'm using 0 and 2 pi because I'm dealing with the sine function, and the two endpoints for the standard sine function are 0 and 2 pi. What do we call this? What do we call this thing that's inside the trig function? It's called the what of the function? Input. There's a more technical name. You might hear me say it. I just want to make sure if I say it, you know what I'm talking about. It's called the argument. Okay? So 4x is the argument of the function. So what you're doing is you're taking the argument and you're setting it equal to 0 and setting it equal to 2 pi. All right? So let's do that. Solve this for x. X is 0, right? Divide both sides by 4. Here, divide both sides by 4. Pi over 2. So what this is saying to me is this. If I plug 0 into this for x, I should be at 0. And if I plug in pi over 2, I should be where? If you plug in pi over 2 here, you should be where? At 2 pi, yes? So that means that my graph has got to look different than this, because when I plug in 0, I'm at 0, but when I plug in pi over 2, which is right here, I should be at the end of the sine function. I should be at the tail end of it. So this was just for reference. Now I'm ready to start trying to graph. So I'm going to put here my graph. I'm going to put 0 here, and right here, I'm going to put pi over 2. These are the two solutions I just got, right? And what I want you to realize is that that is now your entire sine function lives in that little region from 0 to pi over 2. It's got to go through its entire cycle in that period. So because it's a sine function, I'm going to cut this now into 4 equal regions, 5 different points, right? What can you tell me for sure happens here? What should I have right here? An x-intercept, right? Because it's a sine curve, right? I should have an x-intercept here. I should also have an x-intercept at the end. And because it's a sine curve, I have another x-intercept right in the middle. Understand? Now, I just have to figure out now whether or not it does this or possibly this, because as we're going to see, you can get the sine function flipped over. And the way to determine that is just to check a point. All you have to do is test a point. So what was the point right here? This is pi over 4. That's halfway between here and here. What's the point here? Pi over 8. You're taking this and dividing it by 2, basically. If you want, you could say I'm taking this and this, adding them, and then dividing by 2, you should get pi over 8. Is that all right? Let's see what happens at pi over 8. Let's plug pi over 8 into the function. What is f of pi over 8? That's sine of 4 times pi over 8. This fraction reduces, doesn't it? And it becomes sine of pi over 2. And what's sine of pi over 2? Where are you? Pi over 2. Sine is the y-coordinate. 1, right? 1? Sine of pi over 2 is 1. So that means I should, when I plug in pi over 8 into this function, it should spit out 1. So I should be up here. Once I know that, that doesn't really look like halfway, does it? There. Once I know that, I can draw the whole function. Because I know that it must go up like this, then come back down, and then this side has to be below. Now you could check it by figuring out what this point is and plugging it in. Now I'd like to, below this, I'd like to show you something. Here's a very rough sketch of your standard sine function, right? That's your standard sine function right there. Now, this function, if we were to put that onto the same graph, this is pi. Pi over 2 is right here, right? And we just squeezed that entire picture into this little region right here. Here's our x-intercepts, and it went up to 1, came back down to -1, and then back up to 1. So what did that having a 4 here have, what effect did it have on our sine function? It compressed it down, right? It actually shrunk it horizontally, it compressed it. It changed the period, didn't it? It changed how often it goes through an entire cycle. So this number in front right here is important in determining the period of the sine or cosine. This number right here dictates what your period's going to be. So it'd be nice maybe if we had a little formula that told us how that number affects it. We do. So note, given f of x equals sine of omega x, that's the book wants to use omega. The period is 2 pi over omega. Whatever that number is in front of the x, you take 2 pi and divide it by that, and that's the new period. Pardon?
The period we get would be the end point of the graph.
So you're saying that the period here would be the end point of the graph? In this section, yes, but not later. So I don't want to say that. The way that I'm going to have you graph these is exactly the way I showed you. You're going to set the argument equal to 0 and 2 pi, and you're going to solve, and then you're going to draw it, and then you're going to cut it into pieces, and then you're going to figure it out. The period, yes, it does tell you something about the endpoint, but first thing we do is compress these. Then we start flipping them over. Then we start moving them left and right. And then we start moving them up and down. Once you start doing that, then this thing no longer gives you your endpoint. So it's dangerous to say yes to that. All right, so if we look at that problem we just did, if you were asked, what's the period of this sine function, you would take 2 pi and divide it by 4, right? And that would just give you pi over 2. And you can verify it, like that distance was pi over 2. What about just sine x by itself? What's omega? If I said, sine of x, then omega is 1, right? And then 2 pi over 1 is just 2 pi, and that matches what it should be, right? So this is pretty convenient here. Now let's try a different example. Let's try f of x equals -3 sine of pi x. All right, so we are going to use the method that I like to use to graph this, which is do what? I'll list out the steps. That way we have them. Steps for sine, and this also works for cosine, all right, for graphing. All right, graphing, steps for sine and cosine. What's the first thing I said you should do? Those, how do you do that?
Set the first one to 0.
Okay. We're going to set the argument to 0 and 2 pi, because those are the most interesting points on the sine curve, and cosine also. So I'm going to take my argument right now, I'm going to set it equal to 0, I'm going to take my argument and I'm going to set it equal to 2 pi. Here we go. Pi x equals 0. Other equation, pi x equals 2 pi. And from here, what's the solution to the first one? 0. And the other one? 2. Okay, that's kind of weird. That means I'm going to go on a number line and I'm going to start at 0 and stop at 2. It's not going to have pi's in there. Do you see that? No pi's in here. Okay, so I set it to 0. The next thing I do is I mark solutions on a number line. Okay, so I'm going to mark these solutions on a number line. Here we go. 0 and 2. Now notice I marked them and I put actual dots here. Why did I actually put points there? Why did I do that? What kind of curve is this? Sine curve, right? And sine has x-intercepts at the ends and in the middle, right? You have to remember that. So what can I now mark on this picture? At 1, right? So cut this in half, 1, and I can put a dot here. And then I can cut these into halves. This would be 1/2, and this would be 3/2. Do you agree? See how we don't have pi's on the x-axis? It's okay to not have pi's there, right? Now I need to try and draw the graph, right? I know it's a sine. It's either going to go like this, or it could go down and then go up like that. And the way to determine that, I said, was to do what? Pick one of those points. So mark solutions on number line. And then, hold on, plot the x-intercepts. So that's what I did. I marked my solutions on the number line, 0 and 2. I marked where the x-intercepts are, which are at the ends and in the middle, right? And now I'm going to test a point, right? I'm going to test a point for test a point. So the point you pick, don't pick one of the x-intercepts, right? You already know the value. So either 1/2 or 3/2. So I'm going to pick 1/2. And I'm going to plug that into that, right? So when I plug this in, what is f of 1/2? I get -3 sine, and then I get pi, and then times 1/2, right? That's what I get. So do kind of like an order of operations here. This is pi over 2. Sine of pi over 2, 1, right? So this becomes -3 times 1, which is just -3. That's down, isn't it? And it's not down 1, it's down 3 units. So if I were to mark this out, I might not, my graph isn't very good here, but if that's 1 unit, this is about -1, this is about -2, -3 is like down here. By the way, when you're drawing an x and y axis, when you're graphing something, does your scale on the x-axis have to match your scale on the y-axis? Like if this is 1 unit here, does this have to be 1 unit here? No. It has to match left to right though. Like if this is 1, you can't come over here and say this is 10, okay? So I don't have to do this. I could have put -1, -2, -3 right there. But it looked like I could fit it in there, so that's what I did. Understand? Okay, so at 1/2, I'm at -3. Come down here, plot a point. And so right now, I can say that this thing's going to go down, then come back up, and then that means that this 3/2, if I plugged it in, it should spit out a +3. Now, I'm not going to test it, but you could on your own test that. There we go. I don't think I went high enough on that, but oh well. Yeah, I'm not happy with that. That okay? Better? Should mark that out. 3. All right. What is the period of this? What's the period? 2. The period of this is 2, right? Because you can see it from the picture, but also remember that to get your period, you take this, right, and you divide it into 2 pi. So 2 pi divided by pi, that gives you 2, right? That's your period? Yeah? Okay. What is your amplitude? 3, right? Because the distance from here all the way down, that's 6. But if you take half of that, you should get 3. Now, what you might notice, and I'm sure those of you who've seen this before, is that this number right here is somehow actually indicating what your amplitude is. If you take the absolute value of this number, that's your amplitude. So when you just have sine by itself, what's the number in front of it? 1. And the amplitude was 1, right? If we put a -3 here, take the absolute value, the amplitude will be 3. So that's some more information we can throw into our little note here. Remember, go back to that thing I had boxed up. I said given f of x equals sine of omega x. And I told you what the period was, right? The formula for the period. If we add to this an a in front, I don't know if they want me to use capital A or lowercase a. I'm going to use a lowercase a. A times sine x. Right? So if we add a number out front, then the absolute value of a is your amplitude. Is this making sense? Okay. Cosine's a little tricky, a little bit, not much. But so what I'm going to do now is I'm going to give you a problem. Okay. Now I want you to use the method that I just gave you. Okay. I would like to see you demonstrate what I just showed you. All right. You think you can reproduce it? Okay. So we're going to do this on a separate piece of paper, on your own piece of paper. Put your name on it. I want you to graph -5 sine of pi x over 4. I'm going to give you, let's say, 7 minutes. Just see what you can do in 7 minutes. To the best of your ability, use the steps that I just gave you. If you have a question, you can raise your hand. I don't mind helping you out. Or you can talk to each other. I don't... Okay, good. Yep. Okay. Just make sure on your graph you label as much as you can so that I can tell that you... Mm-hmm.
Do I have to take 8 first and then divide by 5 on both sides?
Wait a minute, what did you do?
Should I go like
Divided this.
You can divide the pies out.
So then it would just be 2x.
No, just the pies. Can't
Okay.
divide just the pies first,
So then it'd be x over 4.
and then get rid of the 4. So how could you get rid of that 4? You're trying to get x by itself. Multiply both sides by 4. There you go.
Would I then plug the 1 into the...
Why did that's correct, but why did you stop at 4? Right?
This way, okay,
Yeah.
I'm-
Okay. 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 But what was your next question?
So, like when I fix it,
Yeah.
I plug in
Either
the first
either one, and that'll tell you your yeah.
right? Yeah. So now you're fine. For domains and then
Feel free to list as much information as you like. If you're not going to list it, then make sure on your picture you go up to 5. That way, you know, it's clear that you understand what's going on there. Yes.
would it be something like this?
Yes, sir. Yep. Looks good. No questions? You good?
Well, I figured something. I don't know.
Feel like you're forgetting something?
No, I mean I have something. But
Yeah.
Let's say if it's in the amplitude is 5.
Mm-hmm.
So is it possible that 5? Because that's how I did it. Because last time when I did this, like without calculating the point, the test point, just by looking at the amplitude, can we tell that the amplitude negative could be the same with the down part, and the positive part could be the top part? And for the 5 one, I took it like -5 as the amplitude below, and then the positive part same on the above.
You mean use this to tell you which one starts down and up? If we move it left and right, that won't.
I mean,
that
just for that part.
for if it looks like this, yes.
For looks like this.
Yes, but see, look, if I change this problem and I put in here, this is coming later, okay? So if I say like -4 in here, that's going to move your graph. Okay, it's going to have the effect of moving your graph left or right. So instead of having this, which goes to 8 right here, if we move this, this would actually move it, actually let's go +4. It doesn't matter. This would move everything to left 4. Remember, here's 4, right? So if you move it over, now it's going to go like this. That dotted one is the real graph. And so you can't rely on this -5 to tell you which goes down first. Is that what you were saying? No?
But I'm talking about the y.
Oh yeah, 5 and -5?
Yeah.
Yeah.
I mean, they remain the same, right?
Yes.
I mean, like we took the test point to get like where we go with that
Mm-hmm.
point. Like without taking the test points, looking at the amplitude, can we tell like what would be the y coordinates for those?
Yes. Yes. But if I do this, then no.
Yeah, I changed everything.
Right? So as long as you don't add something out here, you're
Y
okay.
coordinates and then we dash.
Yeah, it'll move up and down. Yeah. Now the amplitude will still be 5, but your y values will change. Yeah. Okay, I'm going to give you like 1 minute. Yes.
Okay, so then
Uh-huh.
that's the 3
Yep.
points. So then I know
Now,
pick a point
pick either one. So take 2 and plug it into the original one.
to plug it into X.
Yep.
Okay.
Plug it in. So you're going to have pi times 2 over 4, right? Or 2 pi over 4 if you like,
It's going this way.
which is
It's down.
pi over 2.
You said 2 pi over 2?
No, that's just pi over 2. Because the 2 and the 4 reduce. And then your sine of pi over 2. So pi over 2 is straight up, y coordinate,
1.
1, and then hit it with a -5, right?
So then it'll be like right here.
Yep, yep. Move it over a little bit underneath the 2.
Oh, it'll be under
Yeah,
that.
directly under the 2, down 5. And then once you know that, you know it goes down and back up, and it's starting from here, it's got to go down, back up. It'll come up to 5 on this side,
Up to 5 up here.
above the 6. Yeah, above the 6 straight up is going to be 5 up. And do you see it? Down.
And it goes
Yep.
this way?
Yep. That's it.
Okay.
Okay? Okay. Everyone feel like they got something? Like they were making progress? Yeah. Okay. We're not going to go through it, but cosine, shall we? Let's see how things change here with cosine. And what I'll motivate this with the idea that we know when we have a cosine, a regular old cosine, there are 4 separate sections, just like with a sine. The difference is that with cosine, we've got x-intercepts here at kind of like the quarter way and the 3/4 way. And then really it's a matter of knowing whether or not it does this, or possibly it's flipped over and it does that. Do you see how that's just a reflection over the x-axis? Yeah? Okay, so let's see if we can let's just work through one of these. The first thing I'm going to do, set the argument equal to 0 and 2 pi again. So I'm set my argument. No, do this back on a different piece of paper. Go back to your notes. 2x equals 2 pi. Setting the argument equal to 0 and to 2 pi.